Welcome to lecture 22 in our class on stochastic processes. Today we will dedicate this session entirely to what is called the Black Scholes formula, which is an explicit formula for the price of a financial derivative on the financial market. It's a very, very famous object in financial mathematics and in economics or microeconomics, in fact. And it was awarded in the 90s, I guess, even with the Nobel Prize for economics. And in fact, it's a wonderful application of the Ito formula and the stochastic calculus that we have learned so far. So it is a very nice field on application of mathematics to a really economic situation. And I hope you will enjoy this application because it's very sound in the end. It's very complete. And it's very neat in terms of the mathematical reasoning that is behind. There was a time when people had quite a negative prejudice towards financial mathematics, and I do not share this point of view at all. I think, in fact, as I have just said, that financial mathematics is a beautiful field of mathematics which brings about very nice problems of mathematical nature with a very direct implication for the real world and direct consequences or direct implications for the real world. So, as I just said, the whole thing today will be dedicated to this formula, and I will explain the contents of the formula as we go along. It is a formula which is obtained inside a model for a financial market, which is called the Black Scholes model, and we will discuss that at the beginning of this section. Namely, the Beck Scholes model of a financial market is a very simple but interesting basic model for a financial market which consists of two assets in which you can invest. One is a stock, which we shall denote with the letter S, which is a random evolution or randomly evolving quantity, namely the price of a certain share on the stock market. And we have discussed the corresponding stochastic differential equation and its motivation. This is the so-called Black Scholes stochastic differential equation for the evolution of a stock, which entails two parameters, alpha and sigma. Alpha is the growth parameter for the corresponding stock process. It would be something like the kind of the mean growth of the value as time evolves if there was no or only little randomness. And then there is another term which influences the evolution of the stock, which is the effect of an exogenous factor or an exogenous market force, which is modeled here in this case by Brownian motion, or better to say by the increments of a Brownian motion, although we don't have quite a very precise concept of that. And so in effect it says that the total fluctuation or the total change in value of the stock at a certain moment of time is the superposition of a total change of value which is following the exponential growth dynamics, which would be this deterministic or drift part, as we say, and on top of that there is an additional kick or an additional excitation due to the external factor, or better to say the changes in value of this external factor, which here in this model is just a Brownian motion. So Wt here stands for the Wiener process or the Brownian motion, and since we shall use the letter B for the second asset in which we can invest, here in this context we shall employ the letter W for Brownian motion. And we do that because there is a second asset in which you can invest in. You can just put your money on the bank account. In the simplest case, we shall assume that the bank account, if you don't change the actual amount of euro, or you don't consume any money that you have on the bank account, or you don't put any money on top of it, so therefore we want to assume that there is a fixed interest rate dynamics by which a 1 euro on the bank account evolves over time, and this fixed income, deterministic income dynamics, is then just given by the continuous or by just the exponential differential equation, where R would be the continuous time interest rate, or just, here in mathematical terms, it's just the growth rate of this exponential dynamics of the bond. B, as I just said, stands for bond, which is just another name for a fixed income, or just a fixed income asset, which just gives a deterministic revenue as time evolves. But you could also think of bank account, which is just more or less the same, at least if we have this simple model. And S, the capital letter S, stands for the stock. So the whole model consists of two components in which we can invest. One is a deterministically evolving deterministically evolving asset, which evolves in a deterministic fashion over time. And then we have this stock dynamics, which, as we had discussed last time, is either described through this stochastic differential equation and a specific initial datum, or the specific initial value, or in other terms is also described by an explicit formula, which we identified as geometric Brownian motion. Okay, so that's our financial market model. It just consists of two assets, and we want to take the perspective, if you like, of an investor or just of an agent in this financial market who can invest into either of the two assets or a composition of the two assets. And the parameters which appear in this model are effectively three parameters, namely alpha. Alpha, as I just said, is the growth rate of the stock if there was no volatility or no stochasticity at all. And sigma is the measure of sensitivity of the total evolution or the total change in value of the stock, subject to the changes of value of this external factor. Sigma is this proportionality factor, and it's called the volatility in the language of financial markets. And R, as I just said, would be the continuous time interest rate for the fixed income asset or for the bank account. And WT is a one-dimensional Brownian motion, and the capital letter W is paying reference to Norbert Wiener, an Austrian-American mathematician who contributed to the theory of Brownian motion at the beginning of the 20th century. Okay, so that's our financial market model. It consists of two different stocks. And as an investor, we, in this financial market, at each moment of time, we may take two positions in both of those assets. And these shall have the letter eta t and beta t for the two positions, namely eta t shall denote the amount of the total number of stocks we own at moment t. That's just number of units, and we shall assume for simplicity that we can buy or own a continuum amount of values of the stock S. Also, negative values for eta are allowed, which basically means that we owe to someone, or we owe just we owe to the market, if you like, the obligation to provide so and so much pieces of that stock. Likewise, we have beta t, which is the number of euro or number of dollars we have on our bank account at moment t, and also beta can be positive or negative, which means that either we have a positive amount, we just have actually capital on the bank account, or if beta is negative, it just means that we owe something to the bank. So likewise, a negative eta means we owe so and so much a stock to someone, which can be some market agency, it can be an abstract entity, but of course it can also be an individual person. So anyway, eta and beta t, this pair, is denoting our position that we take as an investor at moment of time t in these two assets. That's so. If we have just a sequence of values of eta and beta values, then this sequence or this continuum of values is what we shall call a portfolio strategy. And we want to assume that this is, for simplicity, will always be semi-martingales as stochastic processes. So recall that we have a WT here. So we shall assume that we start with a certain probability space that carries this Brownian motion, we will typically work with the sigma field, the filtration which is generated by this Brownian motion. And so we have all this basis for doing stochastic calculus, and we want to assume that eta t and beta t, just for the ability to apply our theory, we want to assume that they are continuous time semi-martingales, or at least predictable. Recall that a process is a predictable process if it can be approximated pointwise in all omega and t by an elementary predictable process. So basically by a process which would be piecewise constant in time, where on each time interval the actual value of the process is determined or is measurable with respect to the sigma field that belongs to the left boundary or the left endpoint of that respective interval. In particular, a left continuous, say, process is predictable. And as I just said, we want to assume that eta and beta are semi-martingales. So that's what we shall assume by a portfolio strategy. It's basically a tuple of two processes which describe the position that we take in each of the two assets. And so the total value of a portfolio obviously would be, so in terms of cash, what it actually means would be this inner product, if you like, of the eta of the portfolio vector with the price vector, which is just the value of the stock at time t times the total amount of stock we own at that moment, and likewise the value of the cash account as it evolves over time, times the total amount in cash we have on that cash account. So that's the total value of the process of this portfolio strategy. And then we shall say that the value is self-financing, the strategy pi, which is this couple of two processes, is self-financing. That's now an important concept. If the change in value of the portfolio is caused exclusively by the changes in value of the two corresponding factors and not by anything else. So that's a core and very important equality. It says that, let me say it again, the change of value of the portfolio is caused entirely by the changes in value of the stock and the changes in value of the bank account, and by nothing else, which means that we don't borrow or we don't disinvest and consume any money. Any changes in the value of the portfolio will really entirely be caused by the changes in value of the two corresponding factors. And I explained this at the beginning of the section when we started doing stochastic calculus, why this is a natural way to describe the fact that the portfolio is self-financing. So it really means that no source of wealth is used in any fashion to provide the changes between the two positions as time evolves. And I should probably interject here generally what I mean if I write such an equality. So whenever I write an equality which involves these infinitesimal increments on two sides of an equation, if you like, this is meant to be as effectively a family of integral equations. So it just says that if I do integrate this equation, the corresponding equality holds for any integration up to an arbitrary moment of time. So which basically means, let me write it like this, it means that for all, if like capital time is t, or probably it's a bad symbol, let me just take, for all possible maximum numbers tau, the integral from 0 to tau of this increment process on the left-hand side, which then after, which by definition is nothing but v tau pi minus v naught. This is the same as the integral from 0 to tau of the corresponding eta s ds s, if you like, plus the integral from 0 to tau of beta s dbs. So it's just an equality of stochastic integrals for all possible limits, or for all possible boundaries of the stochastic integration. So let me say it again, an inequality which involves differentials, this symbolic differentials, I should rather say. Inequality of these differentials is understood in a rigorous fashion always by saying this is in fact to be understood as an equality for this whole family of stochastic integral values that I might obtain. Okay, so that's now the concept of a self-financing portfolio strategy. And one basic question of financial markets is the following. So you can now place a bet on the evolution of the underlying stock. So suppose S, for instance, would be a stochastic model for the evolution of the Daimler-Benz stock. And if you want, you can place an arbitrarily complex bet on the evolution of the Daimler-Benz stock and try to sell that bet on the financial market. Well, sometimes these bets are just made up for playing games and for trying to make profit, regardless the economic or whatever social purpose of such a bet. But sometimes these bets really have a very genuine economic or, if you like, management cause why you would want to place such a bet. For instance, you could think of an investor who wants to buy a certain amount of Daimler-Benz stocks at a certain moment of time, and he wants to make sure that he has enough money to buy them for whatever kind of transactions. So he would like to secure himself by placing a bet and against all those scenarios which would inhibit him from buying so and so many Daimler stocks on that particular day. So he would try to propose such a bet, or he would demand such a bet on the demanding side in order to secure himself. So if you don't call it a bet, but some sort of an insurance, then it makes then it has less of a playing kind of flavor. It is more the thing of practical need, and that's effectively also the origin of such things. So in other words, you could say, I want to formulate an insurance which secures me or which saves me from the exposure to certain risks which come with the random evolution or the random specifics of such a behavior. And such a bet can be arbitrarily complex. And by what we now know, we can just in a very abstract fashion formulate that a derivative, that shall be our basically most abstract concept, a derivative on the stock is just a certain path functional, which if T, a capital T, is what we call the maturity, so this bet will produce a payoff at, say, time capital T. And so the bet, if it is economically reasonable, will be a bet that makes a payoff depending on what we have observed in the entire time interval from 0 to T. So, in other words, a bet, that will be our abstract concept, it's just a path functional that converts the evolution of a path in a measurable way, the path as we observe it from time 0 to T, to a certain output, which is then paid depending on the actual evolution that we had observed in retrospect. And so in the end, a derivative, that will again be our concept, is a path functional which takes into account, for instance, the evolution of the entire path from 0 to moment capital time T, and in this case, the moment capital time T would be called the maturity, typically. Okay, so let us consider some examples of such bets. Of course, the easiest bet that you can place on the evolution of a stock is just to take the terminal value. That's a very simple path functional, but it does fit into our abstract framework. The most famous case, which was originally treated by Black and Scholes in their famous works, is the case of what is called a European call option, which is basically related to this economical situation that I've just tried to describe. So suppose you want to buy a certain amount of Daimler stocks, say in 1 year from now, but you have only K euro per Daimler stock that you can afford at the moment of time, in that future moment. And so whenever the Daimler stock is above that number, you have a trouble, you have in a problem, and you want to secure yourself against exactly that security, is that scenario. So you want to purchase effectively a right so a bet that would pay off exactly that difference towards the amount that you can afford of the actual stock value at the moment time t, but only in the case when you actually need it. And that's exactly this number. So suppose you have k euro at your disposal at time t, and so you can, if whenever the stock price as t is below or equal to number k at time t, again, then you can afford to buy the Daimler stock. If not, then you need someone to kick in and to help you out. And mathematically, this is just described by this function. So you want someone who pays you off exactly this amount of money at terminal time t. And this payoff function, or this bet, or this derivative, is called a European call option. So it's economically reasonable to ask for such a derivative, and it's called derivative because it's a payoff which is generated by some kind of transformation of the initial stock evolution. So therefore, it's a payoff which is derived from observing in some complicated fashion, if you like, the dynamics of an underlying. So therefore, it is called a derivative. Another example, which is can in the end nicely be computed, is what is called the Asian call option, for instance. So instead of asking for the actual value at terminal time of the stock, you take the time average of the evolution, or the time average of the price of the stock on the interval 0t, and you compare that to your to the number k. So I'm not quite sure what would be a practical economic application, but once you are ready to accept the fact that you can place any bet on the evolution, that is still a medium complicated type of bet. But this one, for instance, is different from the previous one in the sense that it really takes into account the full evolution and not only the evaluation of the stock at terminal time. Then you can also discuss the case of the so-called barrier options, which would, for instance, in this particular case, would just guarantee you the payoff of the stock value at terminal time, but only in the situation when the maximum value of the trajectory, when you look backwards in time, has gone above a certain value, k in this case. And that kind of derivative is called a barrier option. And then there's also what is called a numerical option, which is in fact just a whole family of typical payoff functions, which grants you with the right to exercise or just to get one amount of shares, say, at time tau, where tau is a moment of time which you will define as a stopping time by your choosing. And since this amount then is paid off at moment of time tau, then the idea here is that you put the corresponding payoff right into the bank account, which generates an additional growth up to terminal time t, according to this interest rate, according to this continuous time interest rate evolution. Okay, so that is what is called an American option, and it's a little bit of a different object, and which we will touch upon a little later. But you see already by what we discussed in the previous time that this somehow involves the problem of an optional stopping, and it basically can be dealt with the idea of a Snell envelope that we discussed already in the case of discrete time martingales. So, okay, so we will not talk about American options too much, although we will touch upon it. And we will deal with options or derivatives which are really determined in an unambiguous fashion, which means that there's a clear contract which clearly describes for each possible scenario what the payoff will be, and that contract can be arbitrarily complicated. Okay, so this option, as a matter of fact, it can be understood as a privilege, right? So we can think of this phi function typically as a non-negative function. So basically it says that you pay, or you get something if you are on the receiving end of this bet. If you're on the receiving end of this bet, you get a certain amount of money at time t, and this amount of money is contingent on what has happened up to that moment. And as in the case of this investor who can afford at maximum a price of K when at time t, when he wants to buy the Daimler stock or something like this, you would want to be on the receiving end of such a privilege, of such a right. And since people are not nice on the financial market, so if you want to get such a privilege, so someone would grant you such a right or such a claim, then on the giving end there is someone, typically a bank or someone, that offers this to you, that will grant this privilege to you, but that person or that entity will ask for a price. So what's the fair or a rational price for such a privilege? So what's the rational price for a derivative? That's the fundamental question for many, just for a huge branch of financial mathematics. Okay, the question about the price of a financial derivative phi, of course, is trivial in the case when we ask, when there is no time lag between the moment of time when we agree upon the settlement of such a contract and the moment when the contract is generating payoff, because then it's just the same, there's no time lag. So, of course, the interesting question arises because at time zero, we would want to agree such a contract when we have the total absence of knowledge about the future development, and that's exactly why we want, as a receiver of this contract, as a buyer of such a contract, we have an interest in settling the deal, because we want to get insurance, effectively, insurance for something that we cannot entirely predict. Okay, so there is a time lag, and the time at which we want to settle the contract is time zero. So at time zero, the question is, what is the fair price? Okay, and one way to address or to approach the question of a fair, or at least of a rational price, is this concept of a self-financing strategy. We call that a self-financing strategy is a strategy which does not receive money as we pursue it. And so therefore, if you grant such a privilege, so if you want to sell the contract to someone who will be on the receiving end, you could put up a rational price as follows. Namely, you say that the minimal price at which you are willing to sell off this privilege is the minimal amount of money that you need to set up a portfolio strategy at which you set up at moment zero, and which you then will pursue, and which will have the property that at terminal time the value of that portfolio strategy exceeds the amount of money that you owe to the receiving end of the contract, since you sold this privilege. So let me say it again. The rational price for the seller, which is the asked price, would be the minimum cost that you encounter when you want to set up a self-financing strategy, or when you want to pursue a self-financing strategy, which is so that the portfolio value at the end of that self-financing strategy is at least as big as the claim that you have to satisfy. And what is the amount of money you need to set up a self-financing strategy at initial time? Well, the amount of money you need at initial time is exactly the value of the portfolio at initial time, because that's the amount of money you need. So the minimal selling or ask price, if you like, for such a contract, okay, it depends on what is your terminology of ask or bid price, But here I take the perspective of someone who will ask for a certain amount of money in order to actually sell the privilege, who will grant this contract to someone else, who is willing to expose himself or herself to the risk of paying that amount of money. So that's the seller. He sells this privilege, he receives money at initial time for pledging to pay that amount of money, which is described in terms of this derivative phi. And that person could take as a concept for a rational price the minimal amount of cost that he or she needs in order to set up a self-financing portfolio strategy, which is so that at terminal time the value of that portfolio exceeds or is at least no less than the financial obligation that incur to the seller at terminal time. And correspondingly, from the perspective of the buyer, so that's the bid or the maximal buying price of a receiver, so of a buyer of this privilege, would be the maximal amount of money that you need or that you can afford in order to set up a portfolio strategy whose payoff at terminal time is still below the amount you receive if you own the strategy, or if you own the privilege which is described in terms of phi. Why is that reasonable from the perspective of the buyer of that contract to buy the contract if the contract is offered as a price which is no bigger than this supremum? So suppose it's slightly smaller. So why is that reasonable? Okay. Well, if you buy the privilege of the contract phi at the given price, you need to have some money. And the money is then, say, for instance, equivalent or less than the money you can make by selling that portfolio strategy, which would cost this amount of, or which has the value of V naught of pi. So selling that portfolio strategy at initial time just means that you follow the negative of that portfolio strategy. So whenever you have a portfolio strategy which you think of being something that you own, then you just make the corresponding pledge. You sell something that you don't quite own. It's difficult to explain. Okay, before we try to understand why that is a reasonable concept for a rational price from the perspective of the buyer of the contract, let's go back to the perspective of the seller. Why was that a reasonable concept before? Namely, if someone offers you to buy the contract at a price which is still above this infimum of the minimal cost for a portfolio that exceeds a terminal time, if someone actually then is willing to pay you more than you need to set up a portfolio strategy, then what do? Well, you collect the money, you promise you promise the liability phi, or you promise the payoff phi. You receive that amount of money, and you take that amount of money, and you take from that money as much as you need in order to set up a portfolio strategy, which you then can pursue. That's some work you have to do, but it doesn't cost any additional euro, which then in the end, when payoff time comes, when maturity comes, has a value, this portfolio strategy, which exceeds the liability that you have through this contract phi. So in the end, you have completely taken off all your exposure to risk by pursuing this portfolio strategy. And since the amount that you obtained at the beginning of the contract was bigger than the amount you needed to set up a starting portfolio for this portfolio strategy, this means that you made possible gains through this overall business, because you received some money at the beginning of the contract, which you divided into two portions. The one portion goes into the setup of a portfolio strategy, which at the end of time secures you against the liabilities that come from this portfolio, from the contract. But since the amount of money that you received at the beginning of the contract exceeded that minimum amount of money you needed for this securing strategy, you get out of the whole deal with an extra bit of money. And that's why, as a seller of the contract, you accept any price which lies above that number. In order to understand why this definition that we have just discussed for the maximal buying or bid price of the contract phi makes sense, we have to understand first what it means to pursue the negative of a portfolio strategy. Okay, so that involves, for instance, the idea that you own, as in a negative of a stock, for instance. That could happen. By the way, that could also happen if you just play a simple portfolio strategy. So, but at least in the case when you think of pursuing the negative of a portfolio strategy, this idea might come to your mind immediately, what it actually could mean to own a negative of a stock. So the analogy with the bank account is as follows. If you own a negative amount of euro that's on your bank account, this just means that you owe to the bank that amount of money. And the moment when you pay that money back is basically at your disposal. Now, if you own a negative amount of a stock, this just means that you owe so and so many units of the stock to some entity. That entity can be an abstract entity or it can be an individual. And it is your decision when you return this number or this amount of stock. And of course, at the moment when you decide to return that number of stock, the corresponding value of the transaction is determined by the actual value of the stock at that moment of time. But whenever you place a promise to give a certain amount of stock, also whenever you declare that you owe for the first time a stock or a certain amount of stock to someone, of course that person at that moment of time would give you money. So in that respect, it is possible to own negative amounts of euro on the bank account, of course. That's something that we know, and it's also possible to own a negative amount of stock. And the question whether or not a portfolio strategy is self-financing or not, that's a linear condition. And so therefore, if a portfolio strategy is self-financing, so is the negative of this portfolio strategy. Okay, after this, it will be a little easier for me to explain why that number which we have specified here is a reasonable quantity for the maximal price at which a potential buyer of the contract would actually accept the deal. And we suppose that someone offers to buy the contract for less money than it takes to set up a portfolio strategy, which at initial time has that amount of value, which is below that number, and which at terminal time has a value which lies still below the payoff that is guaranteed by the contract phi. Why would you then buy the contract? Well, you do it because you play the negative of such a strategy. So you do the following. So suppose someone offers you the contract for less money than the money it takes to set up the portfolio. So of course, you don't set up the portfolio, but you promise the portfolio. That's how you have to think about it in this case. So by promising this portfolio at initial time, you receive a certain amount of money. Now the price for the contract is less than that amount of time. Now you pursue to play all these negative promises which generate a pledge at terminal time. The pledge at terminal time is to be understood as an amount of money that you owe to the market or to someone, and the revenue or the payoff you get by the contract phi is still bigger than all your liabilities that incurred to you as a result of all your promises. So therefore, you can fulfill all your promises using the payoff of the contract. And so at terminal time, you have no risk at all. You have at most potential gains because the total payoff could even exceed the total liability that you have at terminal time. But in particular, at initial time, when you set up the whole deal, you made a positive amount of money because you gained more through making all these pledges than you needed in order to buy the contract. And that's why the supremum of all portfolio values at initial time, which still lie below in payoff the promise of the contract at terminal time, provided they are self-financing. That's why the supremum is the maximal price under which the seller, the buyer, would still accept the deal. There is a special case when these inequalities here are actually equalities, which is the case when we call a claim or a derivative attainable. And that's the case when there exists at least one self-financing strategy which produces the exact payoff which is described through the contract phi at terminal time. And we will show that in this case the two concepts of price coincide. In this case, the payoff correction, as I just said, the contract or the derivative, sometimes also called contingent claim, is attainable, and the corresponding portfolio strategy, which generates through payoff of the corresponding terminal value, this portfolio strategy is then called a replicating strategy for the contract or for the derivative phi. Now comes the main theorem of this section of our discussion of financial mathematics at all. It's an abstract, or it's a very powerful general statement about the existence and actually the computation of the price of financial derivatives in the two-dimensional Black Scholes model. We call it the two-dimensional Black Scholes model, or some people call it the one-dimensional Black Scholes model, because there's one random component here. Okay, depending on your taste, let's call this for the moment two-dimensional Black Scholes model. So we have these two assets. That's the theorem now, as we had just introduced with these dynamics and these parameters. Then every derivative, that's now the statement of the theorem, every derivative which, for instance, is square integrable, which has finite second moment or finite quadratic expectation, every such derivative is in fact attainable by a unique replicating strategy, and the prices, the ask and the bid prices, they coincide, and they are given by an explicit formula which involves an expected value of the derivative for a very specific dynamics. Namely, I should write this formula, or I should explain this formula in more detail. So it says that in the Black Scholes two-dimensional Black Scholes model, every financial derivative, provided it has this square integrability condition, for instance, is in fact attainable. There is no gap between ask and bid spread. There is a unique replicating strategy. And moreover, the price, the rational price on which both seller and buyer will agree, can be computed by a rather explicit expectation value. And this explicit expectation value involves taking the expected value of the path functional, which describes the financial derivative. When we evaluate the path functional on a very specific stochastic process, which is this geometric Brownian motion that we have discussed and that we have seen as the solution to the Black Scholes differential equation, properly started at the initial time when the observation starts, but with a particular choice of parameters. So the volatility parameter here is fixed, the sigma, but we evaluate this in the case when the growth parameter for the process which is inserted into this path functional is exactly the R parameter, which had the meaning of the interest rate on the financial market. So I shall give you an example of that in a second, but the punchline of this statement is, again, let me say it, in the Black Scholes world, in this two-dimensional Black Scholes model, all derivatives under a certain integrability conditions are attainable. There is no gap between ask and bid spread, and there is a unique replicating strategy. And moreover, we have a quite of an explicit formula which tells us how to compute this price of that derivative, where we have to take the expectation of the path functional when it operates, when it acts on a geometric Brownian motion whose volatility coincides with the initial volatility of the Black Scholes model and whose drift or growth coefficient is exactly the R coefficient, which is the interest rate of the model. And this number here needs to be discounted because it's a payoff at terminal time. So we have to, in the model, we have to, or in the formula, we still have to discount this expected value by the discounting factor that accounts for the fact that the contract typically is settled at initial time. So we ask for the price of the whole thing at initial time. So therefore we discount that future payoff to the time of the settlement of the contract. So therefore we have this discounting factor in front. And one notable thing of this formula is that the parameter alpha, which was the initial growth rate of the actual stock process, that this parameter alpha does not show up at all in this formula, and we shall discuss this in the sequel at several points. So that's a very notable point here. The actual growth parameter of the initial underlying stock price and stock dynamics S does not play any role for the value of that derivative, for the fair or rational price of that derivative. Okay, I want to give an example for this formula, which is actually this so-called Black Scholes formula. Namely, we consider again the case of the European call option, which is a very simple derivative because it involves only the evaluation of the stock at terminal time. And inserting this path functional into this pricing formula, which is the claimed pricing formula of the Black Scholes model, we have that this, well, as I just said, this evaluation is just the application of an exterior function f, which here is this, which is just this tilted or this shifted one-sided absolute value function. So that's, if you like, the function f, which is applied to the stock value at terminal time for the payoff. And so therefore this expected value here is just an expected value which involves the terminal time of that stock. So just writing out what that means, it means that I have to apply this function, this shifted one-sided absolute value function, to this particular stock model with the growth coefficient alpha being equal to R at terminal time. So that's what I wrote out here. It's probably not very nicely written. My handwriting here is not so nice, but it's okay. It's just S naught for the initial time, for the initial position, times the exponential of this process at terminal time, and so forth, minus K. That's again this exterior shift, and then the positive part. Now, since this is involves the expected value of this geometric Brownian motion only at terminal time, which is a transformation of Brownian motion, That in the end is just the expectation with respect to a standard normal random variable, which I can therefore, since Wt is in distribution just like a square root of t times a standard normal distribution psi, I can write this also as an expected value with respect to the standard normal distribution properly scaled. And this way I can write this whole expectation by, if you like, chain rule for our expected values just as an integral with respect to the standard Gaussian kernel, or the standard Gaussian distribution in one dimension, which I wrote out here. And here, instead of psi, I'm writing a u, which is my integration variable after I applied, if you like, the chain rule. And so I see that I have this function, which is a function of the parameter u, and I integrate against the Gaussian kernel. And here I take only the positive part, which means that this whole function inside the bracket, it will start having values only once the parameter u, or the integration variable, exceeds a certain number. Else there is no contribution to the integral at all. And I wrote out this minimal value by just rearranging terms. And so I just wrote out this minimal value after which the term inside the plus operation actually has positive values. And now I see, if I look at this a little closer, I see that this involves a linear factor of something like a remaining integral of the standard Gaussian distribution, which is sometimes called the error function or something. And it also involves an expectation of the same function in the same domain with a certain with this exponential additional factor, which is a term which we basically know from, for instance, computing Laplace transform or something. And if we work out the algebra a little closer, we can write this in simple form as S naught times the error function f at d1 minus k, which is this other parameter, or this threshold parameter, times e to the minus rt f of d2, where d1 and d2 are these coefficients, or these recombinations of the parameters of the model. And see again that here the parameter alpha does not occur, of course, because it wasn't occurring before. And the function f, which appears here, is this error function, or it's just the integral from t to infinity e to the minus u squared, and that's f of t in correction. So f of t is e to the minus u squared du when I integrate from t. Okay, and d1 and d2 are these two parameters. So I do not do the full computation here, but this is just an exercise by which you can convince yourself that this integral here can be, the value of this integral can be expressed in this fashion. And in these parameters, or in this formula on the right hand side, these different parameters, which were r, sigma, k, and t, and s naught, of course, are entering. And what is also entering, as I said again, is this error function, or just this upper integral function for the remaining integral function for the standard normal distribution. Okay, that's an exercise to convince yourself that this is actually true. And in this very short or compact way to express the price of a European call on a Black Scholes market with the corresponding parameters, this is what is actually called the Black Scholes formula for the price of a European call option. And that's the famous formula that you find everywhere. And basically, this is a formula that you kind of program into the simplest of your telephones or programmable computers. And it was really a standard formula for a long, long time on the financial markets and on the actual real world financial markets, by which people were pricing such products. In today's lecture, I want to demonstrate this Black Scholes formula in the probably historically original version, in the original style, which is a combination of Ito formula and some kind of simple economic reasoning, which is the justification for certain identifications we do. And this will be not by applying the general theorem, which is conceptually much broader than the actual derivation that I shall give now for basically the special case of a derivative, which is a derivative depending only on the terminal value of the stock. So let me say it again, this theorem which we had introduced and phrased here a few minutes ago, that's a very nice and very conceptually very compelling theorem, and we will need quite a bit of more material and more auxiliary results in order to show that. And therefore, before I show this very general theorem to you, I want to show to you a derivation of the exact Black Scholes formula that we have seen right now by simpler arguments which use less auxiliary tools in the special case when the derivative, as it is in the case of the European call option, say, in the case namely when the derivative is not quite a path functional, but just involves just an evaluation of the process of terminal time. And that case, of course, covers the European call that is the contents of the subject of the classical Black Scholes formula. Okay, now that's my first derivation, or the first version of the derivation of the Black Scholes formula, in the case when the derivative is really just a function of terminal value, and the derivation here rests upon a couple of assumptions. Namely, if such a contract is settled, then the owner of the contract, for instance, could decide to sell the contract at a later moment of time towards the market. So it's a contract, it's a piece of paper that's worth a certain amount of money in the end, right? So it's a privilege which generates payoff in a not entirely foreseeable fashion at terminal time, but still it represents some value, and therefore the person, the owner of the contract, could decide to sell it. And so at each moment of time we do have some value for that contract, and that value shall be noted by P. So P shall be the price, if you like, from the seller point of view, that would be that he would ask for as minimum price to sell it at time T for this contract phi, which generates then ultimately a payoff at maturity time, as we shall say T. So let me say it again. Pt of omega shall denote the actual price of the contract that the seller or whoever would ask for as the selling price if that contract should be sold at intermediate time T. And of course, at intermediate time T, all kinds of things have happened already. So therefore, that price will, of course, depend on what we have observed so far. And in particular, it will be a random price. It will depend on the evolution that the market has undergone so far. Okay, so there is some price, and we probably would like to know the actual value of that price, but there is, in an abstract sense, there is some price, so there's some value in that paper, in that contract, even before it has generated payoff, but it's a promise of a payoff, so therefore it has value. And Pt of omega is our name for that price at time T in case of scenario omega. So when the market is sitting on the trajectory omega. And we want to make now a structural assumption, namely that this price of that stock, the correction of that contract, is of Markovian nature, which means that here that the actual price of that contract depends on nothing but time and the actual value of the stock at that moment of time. So that's our structural assumption. The price of that contract, which generates payoff at terminal time, when we ask for its value at an intermediate time, will depend only on the moment of time when we ask that, and of course on the actual value that the stock has at that moment of time. So all other information about the stock of the past is obsolete because we ask entirely towards the future. The history of the stock, how it got here, is completely irrelevant for the value of the stock at terminal time. Of course, that's plausible for an option or for a derivative that depends only on the terminal value of the stock. And this assumption is obviously just completely wrong in case when we are dealing with a derivative which really depends in a non-trivial way on the entire path of the evolution of the stock market. But here, in the particular case, that is a plausible assumption. And of course, at terminal time, the price of the stock, the price of the contract is just exactly the payoff that it generates at that particular moment of time. So a contract that generates payoff at exactly that moment of time, the value of that contract at that moment of time is exactly this payoff, and this payoff at terminal time is just encoded through this function f, by which we evaluate the terminal value of the stock. Okay, so therefore, this function small phi, which parameterizes, or just describes as a function the contract value at terminal time, is just the same as the payoff function at terminal time. And here I'm having a misprint because I should write here just the function f, because the function f as the description of the output has no t dependence. It's just the function that describes in terminal time how the value of the stock is translated into a payoff under the contract phi. Okay, and now we want to assume that there is a replicating portfolio. So we think that there is a portfolio whose terminal value coincides with the payoff under the contract phi, and hence for intermediate moment of time, if there is no cheating going on, the fair price on which everyone would agree as an equivalent for the value of that contract is exactly the value of the portfolio at that moment of time, the value of that portfolio which we see when we pursue that portfolio strategy. That makes absolutely sense, because we have, if I have that, pursue that portfolio strategy, and if I look at that portfolio at an intermediate time, then at this intermediate time the portfolio is again a portfolio which after that will generate. And so at that moment of time, the owning that portfolio or the contract is just the same, because at terminal time they generate the same payoff. So therefore, the portfolio value, the value of the replicating portfolio at terminal time is the same as the price of the contract at intermediate time, and by our formula or by our assumption, this price is given by this exterior function phi, this price functional, evaluated at time t, evaluated at stock value st. So that's, if you like, some sort of a no arbitrage argument, which means that if you have a portfolio which generates exactly that payoff, then the price for that privilege that comes with that payoff is just the same as the portfolio. Else, if the two sides agree on a different price than this value of the portfolio, you could basically produce some gains without any risk, depending on who's paying too much. Okay, now we want to assume that the portfolio is self-financing, so therefore by our basic assumption, or just writing again what this actually means, is that the infinitesimal increment of portfolio value decomposes in this fashion. And let me say it again, this is in formal writing with these infinitesimal increments is a formal writing of a whole family of corresponding equalities for the corresponding stochastic integrals. But in the future we shall get used to this shorthand writing for these stochastic integrals, because that's you will see it's an intuitive way to deal with things. Okay, now since these S process and the B process both are defined through or known to satisfy certain stochastic differential equations, we can expand this equation a little further and just insert the corresponding increments according to the dynamics of the Black Scholes model, which means that the ds increment is a sum of an alpha s dt and a sigma s dw, and the bt increment is rbt dt, where r is the interest rate. Okay, that's one side of this equation. But on the other end, this is the increment of the phi process, because v and phi coincide. And by Ito's formula, this v, if I take the infinitesimal increment of that, applying Ito formula, I get all kinds of derivatives, or the chain rule, if you like, but the corrected chain rule for this object, if I take the infinitesimal increment in time. Now, the infinitesimal increment in time of this phi, which is the same as the infinitesimal increment of the dv, by Ito's formula, is the first order infinitesimal increments, if you like, where, of course, I keep in mind that this ds thing here, when S is a stochastic process, is generally not a conventional infinitesimal increment. So the first order chain rule is then that you take first order derivative of this function phi in two variables with respect to the first variable, and you integrate with respect to the change of the first argument, then, or the first component. Then you take the first order derivative with respect to the second component inside the function, and then you need to integrate with respect to the increment of the second component. And then we have, by the Ito correction, we have to consider all possible second order derivatives of this function phi, which is a function of two variables. But by similar reasoning as we did already before, there is only one term in all these second order derivatives that meets a non-trivial integrator, namely the bracket here for the second order derivatives is needed, and there's only one case when the bracket is non-trivial, which is when we take the bracket of S with itself, which means that I take the second order derivative in the second diagonal direction, because all other brackets or co-brackets involve a bracket with the T process, which is a process of zero quadratic variation, so therefore those brackets disappear and don't contribute. Okay, and now I just insert, if you like, my knowledge about the S process again. The S process is a semi-martingale, which has, again, a component of finite variation and one component of finite quadratic variation. So first I expand this ds according to the law of or according to the specifics of the dynamics of the Black Scholes model. That's the ds expansion, which gives me an alpha s dt. There is another second summoned for this ds expansion again, which is the sigma st dwt. And then I have this Ito correction term, which involves only one second order derivative, and the bracket of the S process with itself, by just inserting the equation for the S is just sigma squared s squared dt, because that's the part which comes in front of the w. So recall that the ds, do I have it here? Right. So the ds, in terms of the Ito formula, the increment of the ds is has only one component which is not of non-zero, which is not of zero quadratic variation, which is the component which is in front of the Wiener process, and that's in quadratic variation produces a sigma squared st dt by the Ito isometry, if you want. So rearranging terms here on the right-hand side according to whether they appear with an increment in time or an increment regarding Brownian motion produces just this formula, where just rearrange terms. And I remember again that this was supposed to be the same as the increment of this self-financing strategy with these linear sum of increments of the dB and the dW, ds process. So I just confront this with the previous first formula, where I do a rearrangement of these terms. Let me say that again. So we were starting with this correction. We were starting with this representation of the increment of the portfolio value process, and this representation here involved also two terms or two stochastic integrals with respect to the time and one stochastic integral with respect to Brownian motion. So I rearrange that formula also according to these two parts, and what I see is that I have an equality of two stochastic integrals with respect to a semi-martingale. One is a stochastic integral with respect to time axis, and the other is a stochastic integral with respect to a Brownian motion. Now, since this is all still on an ansatz basis, I don't need quite to justify this, but I'm just equate now the corresponding integrands of the respective two stochastic integrals. So I'm saying I surely have an equality of the two quantities of the two semi-martingales if the respective two integrands in these two integrals on the left and on the right hand side, if they are each the same when I separately consider the dt part and the dw part. And this, in the first step, would suggest that if I really want to have equality, then I would want to have that the coefficient in front of the dwt should be same on the left-hand side and on the right-hand side. And I see that on the left and on the right-hand side in front of the dw, I have certain factors where some factors already coincide anyway. So I can make sure that the two stochastic integrals with respect to Brownian motion are the same if I just choose as my first ansatz the eta, which is the component in the stock of my portfolio strategy, coincides with the first order derivative of this function phi in the x direction. Why not make this choice? If I do make this choice, I can at least convince myself that the two stochastic integrals, which are equated here in this equation, that these two stochastic integrals coincide at least in the part that involves the integral with respect to Brownian motion. Now I can insert this choice of eta into the comparison of the integrands which are integrated against the dt part in those two sides of the equation. And this means the following, namely, if I consider this, let me see it again. If I consider this phi x now as my eta part, then I see that eta times st is exactly the part that measures the total value of the stock part in my portfolio value. So I can replace this part phi sub x times st. This is a part of my total portfolio value, so it's the phi value which was assigned, which was the number or the value of the stock, the value of the portfolio at that moment of time t. And what I really did here, by the way, sorry, is I wrote that this, let me see it again. All right, I'm sorry. So what I did here is, all right, so, sorry, I did something else here. So I looked at for the comparison of the dt parts, in order to close the equation, I look at this product of beta t times bt. Beta t times bt is the value contribution to my portfolio value of the bond part. So therefore bt times beta t can also be written as the value of the portfolio, which was my phi, minus the value of the stock component of the portfolio, and the value of the stock component of the portfolio was eta times st, but eta is the same as phi x. So therefore, after I did this choice of eta, the dt part on the left-hand side, or the dt, the integrand, which is integrated against the dt on the left-hand side, can be equivalently written like this. This is the left-hand side of this is the left-hand factor in front of the dt, and the right-hand side, and the factor in front of the dt on the right-hand side, I write out in an unchanged fashion. So if I make sure that this relation holds true for the corresponding integrands on the left and on the right-hand side, which appear in front of the dt integral, then altogether I can really make sure that this equality, which is here, is actually satisfied. So the argument here, let me say it again, was the following. So if I claim, or if I think that there is a self-financing portfolio value, a portfolio strategy, then I can combine the two requirements, or I can combine on the one hand side the claim that the portfolio strategy be self-financing with, on the other hand, the Ito formula for the representing function. I can combine those two types of information in order to write down two sets of conditions for the strategy on the one hand side, eta, and on the other hand for the function phi to be satisfied in order to really fulfill the two conditions altogether, the two conditions, or the self-financing conditions, and the Ito formula. So if I then rearrange the second condition, which if you look at it is a condition which involves certain combinations of partial derivatives of this phi function, I end up with a relation among the first and second order derivatives of the function phi as follows. Namely, I want for this to be true that the partial derivative of the phi function with respect to time is equal to this combination of first and second order derivatives of the function with respect to x, where I have in particular a second order derivative with respect to the function x, which comes with a prefactor, with a negative prefactor. This is, suppose that these two other parts here in this equation on the right hand side were not there, then we would be dealing with basically a parabolic or just a heat equation with some nonlinear mobility here on the right hand side, which would be just more or less like a heat equation or a version of the heat equation, but only in the case when the factor, when the minus sign wasn't there. And that's why we consider this as a heat equation in negative time, and I shall come back to that in a little moment. So that is a parabolic equation, but which comes with the wrong side, if you like, with regards to the second order derivative. So that's why we consider this as a parabolic equation, which is in inverse time. And what we at the end also then, or what we are in particular at the end also require, is that this function phi satisfies this equation for the corresponding investment strategy or portfolio strategy to be self-financing. And also recall that we had this requirement at the very beginning that at terminal time this phi function is equal to the function f, which describes the payoff of the contract at terminal time. So altogether, these two conditions set up a partial differential equation, or to be precise, a boundary value problem. They set up a boundary value problem on a certain part of the time of the product of the non-negative time axis with the Euclidean line. So that's the real axis, and here we have the time axis, and we have, in fact, here this in the green box we now have a boundary value problem, which consists of finding a function phi, which at a terminal time t coincides with a given function f, which describes the payoff of the derivative. And what we are looking for is the function which solves this PDE and for all times which lie below 0 and this capital time t. And this is the Black Scholes boundary value problem. As a PDE problem, it is an inverse in time PDE parabolic problem. In a way, we have backward engineered this equation, this partial differential equation for this function phi. And we have derived this equation, this partial differential equation for the function phi, using, let me say it again, the Ito formula and the requirement that the corresponding portfolio strategy be self-financing. And we can convince ourselves of the validity of this condition, this PDE condition on the function phi now as follows. And that would be, if you like, the forward conclusion, namely, putting aside all the previous considerations, let us formulate it as follows. Let phi be a function which is, say, continuous on this piece of the time and space domain, and it is twice continuous differentiable, say, in the interior of this domain, and assume that this function phi satisfies this Black Scholes partial differential equation. And let us furthermore assume that at terminal time this function phi at terminal time t coincides with a given boundary function f, which is a boundary function in the sense of a PDE. Then we can make the following choice. We define the process eta of t, which is obtained by taking the partial derivative of this function phi with respect to the x component, and insert that at moment of time t, we insert the value of the stock at that moment of time, st. That's a certain random process now, and we call this random process eta, and assume we define a random process beta of t, which is obtained here in this form. We take the phi function, we subtract from this the phi x, the derivative of x, so there's the eta minus st times st, and we divide by the value of the bt process, which is a positive process. Then that's the claim. If we interpret these two stochastic processes as the components of a portfolio process, then this is a continuous process, and particularly is predictable. And then the statement is that this is in fact a self-financing portfolio strategy for the two-dimensional Black Scholes model, which is defined by means of the parameters alpha, r, and sigma. And in particular, it is so that the terminal value of that portfolio strategy coincides with the payoff of that derivative, which is encoded by means of the function f on the terminal value of the stock. Okay, that would be the forward conclusion of the derivation, which was formal before. And the forward conclusion can now be obtained as follows, namely first, the value of the stock, the value correction of the portfolio strategy, according to our definition, would be beta t times bt plus eta t st. That is just the value of the portfolio at time t. And if you look at, in particular, at the definition of the beta t, it just produces, by this definition of beta t, it just produces that the value of this portfolio strategy at any time is exactly equal to the function phi when composed with the process st. That's because we have just put that phi here in the denominator and the numerator of that expression. And by the condition that at time capital T, the function phi coincides with the f function, we have that at terminal time this portfolio value is exactly the value of is exactly the payoff of that derivative. And we can now check whether that portfolio strategy is self-financing. Well, we have this expression for the value of the portfolio strategy. So in order to compute the increment of that portfolio value, we just apply the Ito formula as before. And then we do the algebra as before, essentially. We insert what we know about the increments of the S process. We write down the increments of the S process, and of course through the Ito formula, the partial derivatives of the phi function reappear. And then we can just recombine the terms and do exactly the same computation that we did before in order to derive these conditions on the partial derivatives on the function phi, in order to end up with the conclusion that before we had started with. So this is just, in fact, the backward or the forward engineering of the calculation that we did just before. So in fact, this main proposition or lemma is then true, that if we have a function in two variables, time and space, which satisfies this particular PDE, then this choice of coefficients eta and beta, which involve basically the derivatives of this function phi, they generate a portfolio strategy which is then self-financing, and it's made in such a fashion that if the boundary value of phi coincides with the f, then actually this portfolio value equals the payoff at terminal time. So that's the core here. And in order to make practical use of that, okay, stop at the moment, except for a while here. So this, what does it tell me? This tells me that in order to compute the value of the portfolio, which is the same as the value of the derivative, basically what do I need to do? I need to solve a certain PDE that is a backward in time PDE, and whose terminal boundary value function for the terminal time is determined through this specification of the of the payoff and the option. And then if I want to evaluate the value of that contract at any intermediate time, I just need to take that function phi at this moment of time and insert the stock value that I observe at that moment of time in order to get a closed form solution or closed form expression for the value of the contract, for the rational value of that contract. And in particular, I get an explicit construction what I need to choose for my replicating strategy. That's an important additional virtue of this approach, that this gives me a very concrete and pretty precise algorithm, in fact, how I need to set up my self-financing strategy, which would reduce all my exposure to risk. Because this is exactly what I have to do. I can implement this on a computer. Once I have this function phi, I can just put all these formulas into a computer, and the computer will do all the remaining work for me and produce this self-financing strategy. And all my work is completed. I don't need to. I can go and I can go to sleep and wait until maturity comes, just giving these formulas to my computer. So that's another very strong virtue of this approach. The final result of today gives away how to compute without asking a PDE person this value or the solution of this Black Scholes Pde in a way, by using stochastic calculus again. This is in a way reminiscent of what we do in order to solve the Dirichlet problem for the Laplace problem, or the Dirichlet problem for the Laplace equation on a bounded domain using expected values with regards to Brownian motion. Now we do a similar thing, but now this time for a time-dependent PDE, namely the Black Scholes Pde. And the lemma here goes as follows, namely let phi be a solution to the Black Scholes Pde on this piece of a time-space domain. Then for all positive initial values of a certain process, S tilde, which is our hero of this lemma, the corresponding process which is obtained by inserting this new hero S tilde into the phi function at time t and multiplying the whole thing with an exponential factor e to the minus rt, then this whole thing as a function in t, as a random function in t in fact, is a local martingale, where S tilde, that's the hero here, is again a geometric Brownian motion, namely a geometric Brownian motion with volatility sigma and drift r. So here we have this geometric Brownian motion popping up, which is a geometric Brownian motion with specifically the drift parameter being equal to the deterministic interest rate. So the lemma is, I can, if I have a certain solution to a time-dependent PDE, which in this case is the Black Scholes linear PDE, then I can look for a process, which in this case is a geometric Brownian motion, such that if I insert this process into this function, which is now a time-dependent function, and if I multiply, if you like, with a little other function, which is time-dependent, then this whole new process is a local martingale. That's a very nice thing whenever you observe such a thing, because basically it tells you that you can express this function, this unknown function phi, by evaluating this martingale at different times, and we will see that in a second how that goes. But let us check the validity of this lemma first. The validity of this lemma will be shown by applying the Ito formula, of course. Namely, we have, if you like, a function which accepts three inputs, alpha, beta, and gamma, and it returns e to the minus r alpha times phi of beta and gamma, where alpha and beta in this case are both the stochastic process, which are just the constant, or the identity in time functions on processes t, and as gamma we choose the S tilde process, so this new hero, this geometric Brownian motion. Okay, so we want to show that with this choice of input processes, input process component X, the corresponding composed process is at least a local martingale, and we do that by writing out the infinitesimal increment, or writing out basically the Ito formula for this composed process, and we try to convince ourselves that this process is just evolving through an integral of a martingale. Okay, so Ito formula again tells us that we have to take all first order derivatives with respect to all components of this combined function and integrate with respect to the corresponding component or the increments of that infinitesimal increment. So taking the first order derivative with respect to the first parameter or first variable of this capital F function is the derivative with respect to that parameter. So that's in minus r e to minus rt times dt. So it's only the derivative in this part. Plus the derivative now with respect to the second parameter here is a phi dot t times t s tilde t dt. Then I have the derivative of first order with respect to the last variable, which here is the x variable. So, and then I need to integrate with respect to the increment of this last component. And then I have the Ito correction term, which here again involves only the second order derivative with respect to the last component, because all other components or combinations of that involve terms which have vanishing quadratic variation. And so only the bracket of the S tilde process with itself will appear in this Ito formula. And since the ds tilde has this representation as a geometric Brownian motion, as we know, we can expand the ds tilde further, and the ds tilde comes with an r times s tilde dt, and this is collected among all other terms with a dt integral. And the bracket process of S tilde with itself, again, here is only the contribution from this stochastic integral with respect to Brownian motion, and that gives me a sigma squared S tilde squared as a factor. So that gives me a sigma squared S tilde squared. So that collects all the dt parts here in this formula, and I have also this first order derivative from the Ito formula with respect to the x component, which is then integrated against sigma s tilde dw tilde, again from expanding the ds increment. Okay, and I see that inside the dt bracket, inside the integrand against which is integrated against the dt, this integrand is a combination of exactly those terms which appear in that fashion in the Black Scholes Pde. So therefore I have a 0 here in front of the dt, and the only stochastic integral that remains, if I write that, if you like, as a stochastic integral, is the integral of that stochastic process with regards to the Brownian motion, which is a local martingale. So that proves the claim. And if we furthermore assume that this is not only, that the function phi is not only any solution which is continuous, but suppose for a moment that it's also a bounded solution, that's more like a technical assumption at this point, then we can actually give an explicit formula for this price of the derivative by performing an expected value as follows. Namely, if we have such a solution to the Black Scholes Pde with the corresponding boundary value as specified through f, then this value of the corresponding derivative is then given by, as we know, by the value of the phi function, which is the solution to the Beck Scholes Pde at initial time, evaluated at the value of the stock that we have at initial time. But then that's now the new piece. That is then the same as the expected value of the terminal function, the payoff function, against the terminal value of the new hero, of the geometric Brownian motion with the right drift. And why is that so? Well, this phi process, or this process is part of this is the statement of the previous lemma. This process that we have here is then a martingale, and therefore the expected value of this martingale is constant over time. If we evaluate this martingale at time t equals 0, we get exactly the expression that we are asking for. It's phi at 0 at the position s naught tilde. And the expectation of that process at terminal time is exactly phi equal capital T s tilde t, and phi at capital T is just the f function. So that's this argument is pretty much the same in essence as the argument that we used in order to identify the solution of a PDE through an expected value of an appropriate process. So that's exactly the same idea here, that this function can be obtained through this expected value by the constancy of expected values for martingales, and using the fact again that at terminal time this function phi of t equals function f. And now you see that we have confirmed in this special case exactly the Black Scholes formula which we discussed following our abstract result about general derivatives. And here we have justified this result in a very hands-on fashion, just using the Ito formula in clever fashion. So this formula here is exactly the formula that was our point of departure for the exact Black Scholes formula for the price of a European claim in a two-dimensional Black Scholes model. If you recall, that was this starting point here, namely the price here is exactly this expected value for this payoff function. If you compare this expression, it is exactly the term or the quantity which we have written here. And let me say it again, we have given a full justification for the Black Scholes formula for a simple derivative using just clever fashion, the Ito formula. This was the historically first derivation of such pricing formulas, but the theorem and the method goes much beyond this class of very simple derivatives, and that will be the contents of the next lecture. But we will need some more mathematical technology, which will be very important in other contexts outside of financial mathematics as well. And therefore we might first do these abstract mathematical things before we come back to the Black Scholes world and prove actually this much more abstract version of the pricing theorem for derivatives in the Black Scholes model, which I showed to you once more. It says that in the two-dimensional Black Scholes model, any whatsoever complicated derivative has a unique price. It even has a unique replicating strategy, and the price of that derivative is given by computing the expected value of that payoff, but on the right stochastic process, which is not arbitrary, but which is the stochastic process, which has the drift according to the interest rate of the model.